A couple things to remember. Number one, hypotheses are statements about a parameter, not about a statistic. If your hypotheses have statistics in them, that is very, very bad. Hypotheses should only have parameters in them. Why is that? Because the parameter is a thing that is unknown that I can't get my hands on. That's what I'm hypothesizing about. The statistic, I know exactly what it is. There is no guessing to it. The statistics come from the data. There's no guessing. And I've kind of tried to summarize that here for you. The whole point is to see what you can infer about an unknown parameter based on a sample statistic. You've heard me say that countless times now. It's the whole point of this course. And so I should be hypothesizing about a parameter, not hypothesizing about a statistic. Number two, p-value is not the probability the null is true. It's not the probability the null is false. It's not the probability the alternative is true. And it's not the probability the alternative is false. Rather, it is the probability of obtaining such an extreme sample result if the null hypothesis were true. It's the probability of what are the odds that we got something as wonky as we did. Okay. And the last thing to remember, we do not accept the null hypothesis, but rather we fail to reject the null. And so it's at this point that we have all of the pieces together that we need to work a hypothesis test. We've done them all piece by piece, and I want to kind of summarize that here for you at the end of this video into one handy page of notes. And I want to do it before we start writing it down because I don't want us to get ahead of ourselves here. I want to just reverbalize everything that we talked about. And if you have a question about one of these pieces where you pause and go back and watch that part of the video, whether it's this video or the one before, because all of these individual pieces are their own mini lessons. But now we've just got to put all those mini lessons into one thing. So what we're going to do is we're going to start off by trying to find our null and alternative hypotheses. Remember that the hypotheses will always have three pieces. They will have a parameter, they will have some mathematical operator, and they'll have some number. Okay, the parameter and the number are going to be the same for the null and the alternative. The only difference is going to be that mathematical operator. We're going to find a test statistic. We do that by standardizing the sample statistic of interest. So it's going to be standardizing it very similar to how we did in chapter 7 with one tweak that we'll talk about when we get to this slide. Okay, we're going to standardize by taking a value, subtracting its mean, and dividing by its standard deviation. Under the assumption that the null hypothesis is true, that's how we work all hypothesis tests. We can work the problem one of two ways. We can use the rejection region method or the p-value method. The rejection region method, you draw your little picture, shade to the right, shade to the left, or shade in both if it's two-tailed, and say, did our test statistic lie in the rejection region? If it does lie in the rejection region, that means you reject the null, conclude the alternative. If it does not lie in the rejection region, fail to reject the null, cannot conclude the alternative. You can also use the p-value method. P-value is the probability of getting a test statistic as extremely more than the one we got from the sample data under the assumption that the null hypothesis is true. Again, make sure you know that. Right, it's going to be finding a probability using a Z or T table using Excel. And if that p-value is really small, specifically less than alpha, then we're going to reject the null hypothesis. That means we conclude the alternative. If it's large, specifically greater than alpha, we're going to fail to reject the null. And we're going to say we cannot conclude the alternative. And then, of course, the last thing that we have to do is that we have to make sure our assumptions hold, right? Just like we've done here in the last couple chapters, we have to say, when we standardized that statistic of interest, did we have normality? When we standardized p-hat, was p-hat normal? When we standardized x-bar, was x-bar normal? Okay, so we have to check our assumptions. Did we get that normality that we thought of, that we thought we had? And specifically, we have to make sure our sampling methodology is sound. We have to make sure that we don't have any of those biases that have crept up. Why is that? Because now that we're dealing with samples and making inferences on populations, we have to say, is my sample actually any good? Right? Because if I did all the math right, but my sample actually is garbage, I mean, you know what they say, garbage in, garbage out, right? So if my sample isn't very good, then I have to talk about that and say, yeah, I could do this work, but my sampling method was bad. And so that means my results may not be that good. So we always want to come back and check those assumptions. Okay. So we're going to put all that together here on this next page. Step 1, determine the null and the alternative hypothesis. You have three options. You can have the null is equal to, the alternative would be not equal to. Again, parameter and value are going to be the same. Right now we're talking mu and p. Here we're talking whatever number comes from the problem. You can have a left-tailed test. That'd be right here because we always call it based off what the alternative is. If we have a less than alternative, it's a left-tailed test. That means the null is going to be greater than or equal to. Or you could have a right-tailed test. This would be a greater than test. That means that the null is less than or equal to. I'm calling it step 2 here. It could be step 2. It could be step 6 or 7. There are dozens of ways this can be described. The steps, the numbers of what they are is not pivotal. You will not be tested over what step is what. I'm not going to, test you. What's step 4 ask for? You can do this as a 3-step problem or a 6-step problem or a 9-step problem. Doesn't really matter. So I've called it step 2 here. It may come at the end. It doesn't really matter if it comes here. Sometimes we like to check our assumptions right off the bat. Sometimes we do it at the end of the problem. Doesn't really matter. Somewhere we have to check our assumptions. I put the word conditions. Conditions and assumptions are synonymous. Okay, if I type one or the other, I need you to know they mean the same thing. I'm not trying to trick you. It might just be that day that was the word that came to my head. Okay, so conditions, assumptions, same thing. First thing, like we said, we're always going to check to see if we have sound sampling. Again, check those biases that we talked about in chapter 1. Do we have any of them or not? Do we have a representative sample? Or do we not have a representative sample? Then we have to say, is the statistic that we're standardizing normally distributed, right? So is p hat normal or is x bar normal? So for proportion problems, we need p hat to be approximately normal. We need to check if x is binomial. And we need to check, like we did before, n times p and n times q. Now, the only adjustment we have to make here is that if we are assuming that the null hypothesis is true, then we're going to assume that the value for p in the null hypothesis is what p actually is, because we don't know what p is, right? Let's think about this. If we're doing a hypothesis test, we're hypothesizing in the null, say, that p is equal to 0.5 or 0.75. It doesn't really matter, right? Whatever the problem says. But we're assuming the null is true, so we're going to assume that value of p is true. And so I'm going to simplify that here as p naught. And then 1 minus p naught would be q naught. Okay, so just a subtle shift from what we had back when we did this in chapter 7, when we did probability questions. There we had a value for p and q, and so we just did n times p and n times q. Now we don't know what p is. That's the whole point of the problem, right? The whole point of this is I don't know what p is, and so what do I use? Well, I use the value that came from the null. Right here, I'm going to scroll back up. Whatever that value was right here in the null, that's the value that we're going, this right here would be p naught if this was a proportion problem. If it was a mean problem, it'd be mu naught, right? It's just saying whatever that value was, okay? Then for mean problems, we need x bar to be normal either exactly or approximately. It doesn't really matter, it doesn't really matter how we got there. It doesn't affect our math as long as we get there via exact normality or approximate normality. How can we do that? Remember, we have that gated approach. If x bar is normally distributed, if x is normally distributed, then x bar is normally distributed. That's what this first one says right here, that we get there. What we need x bar to be normal if we started off with normality. If that doesn't work, we go to central limit theorem next. We say that we get to that approximate normality if the central limit theorem holds true, if we have a large enough sample size to overcome the skewness in the distribution. We have to find a test statistic. How do we do that? We standardize the appropriate sample statistic. So if we have a proportion problem, that would be p hat. Notice this looks very similar to the work that we did in chapter 7, except as we did before, I'm going to tack on that little naught to every p. Again, just like we did in the assumptions, we don't know what p is. And so what do? We take the value that came from the null hypothesis because we're assuming the null hypothesis is true. And then for a means problem, it's going to look very similar to what we did in chapter 7 as well, except as we talked about, if we don't know sigma, which is a very realistic world, why would we know sigma, right? If we don't know what mu is, we're going to instead use S to replace it. And because we use S instead of sigma, that gives us a t test statistic. And so we're going to take x bar, we're going to subtract the value of mu that we find in the null hypothesis. We're going to divide by S that came from the data, divide by square root of n. So very similar to chapter 7, except in chapter 7 we were given a value of sigma. In this case, we're probably not going to be given one. We're going to have to use S instead. Then we can talk about our rejection region and or our p-value. So just as a reminder, we've already covered this, but we call the test left, right, or two-tailed based on the rejection region. The rejection region is based on the alternative. If the alternative is less than, we have a left-tailed test. If the alternative is greater than, we have a right-tailed test. And if the alternative is not equal to, we have a two-tailed test. And that's also going to be how I draw the rejection region. Then determine if we have statistical significance. Statistical significance is if we reject the null hypothesis. So determine if we can do that or not. We say the following statement: because our test statistic falls in the rejection region and the p-value is less than alpha, we reject the null hypothesis. Or we're going to read all the parentheses statements. Because our test statistic does not fall in the rejection region, the p-value is greater than alpha, we fail to reject the null hypothesis. So make sure you understand what I'm trying to get at here. You have one of two options. Option A, because our test statistic falls in the rejection region and the p-value is less than alpha, that means we reject the null hypothesis. Your other option, because our test statistic does not fall in the rejection region and the p-value is greater than alpha, then we fail to reject the null hypothesis. This is what I like to call the nerd hypothesis. I would call it that because it's got all the symbols in it. It's more mathematical based. It uses language that the layperson would never use, right? We would never really talk about rejecting or failing to reject the null in your common conversation. It's important from a statistical standpoint, but it's not extremely practical. The conclusion is what's practical, and that's where we talk about the alternative. Remember, if we reject the null, we conclude the alternative. If we fail to reject the null, we cannot conclude the alternative. And that's much more practical and meaningful, and that's how we're going to conclude. We're always going to follow up with, did we reject or fail to reject, with what did we do with the alternative? And so I'm going to say here our conclusion is at the blank % significance level, there is sufficient evidence to conclude the alternative, or at the blank % significance level, there is not sufficient evidence to conclude the alternative. Again, if you said reject, there is sufficient evidence, you can conclude. Those are synonymous statements. If you fail to reject the null, then you cannot conclude, or you say there is not sufficient evidence. Either one's fine. Those are synonymous statements. Except notice in the previous sentence, I've just left it as H naught. You don't have to write it out. That's common vernacular to say reject H naught or fail to reject H naught. However, in our conclusion, notice I've put H1 in those square brackets. That's important. That's because I need you to write out the alternative in words. Okay, it's not a situation where we write H1. It's not a situation where you write the words the alternative hypothesis. If this is a conclusion that makes sense from an English standpoint, you need to write the alternative out in words like from an English standpoint. Okay, again, the first part of the slide is more of our mathy answer. The second part's the one that you might say to your boss, or you'd say to a colleague. You'd say something that makes more sense from plain English. And so instead of saying I can't conclude the alternative, you're going to say I can conclude that the true mean weight of puppies is greater than 25 pounds, or whatever it may be. Okay, and the key here is that we need to make sure that we say we have a parameter, you say the right symbol, and you say the number. Remember, the alternative hypothesis has three pieces. It's parameter, has mathematical operator, and has a number. And so when you write out parameter, there's actually three pieces of parameter. One is you have to have a population word, right? Whether that's true, all, known, real, something of that nature. You have to indicate that it's a parameter by one of those population words. Then you have to tell me what kind of parameters. Is it a mean or is it a proportion? So one of those two words need to be there. You can use average instead of mean if you want, or you can use percentage instead of proportion if you want. And then again, context of the problem, mean what, right? You can't just say the true mean what, right? Age, weight, height, whatever it may be, proportion of what? Proportion of people who are going to vote for a certain candidate, proportion of people who made a certain grade in a class, whatever it may be, right? And then the alternative, again, you only have three symbols in the alternative. You either have greater than, less than, or not equal to. So you're going to say is more than, is less than. In the not equal to case, it's more acceptable from an English standpoint to say is different from. That way we avoid a potential double negative. So we'll say more than, less than, or different from, depending on what the alternative is. And then whatever the number is to close this off. And then while we're here, just one last thing here to point out is that going back to that idea of type 1 and type 2 error, because it's one of the most confusing concepts of this chapter. A type 1 error is rejecting the null, but the null was actually true. Notice when you decide to reject the null because the test statistic was in the rejection region and the p-value was small, right? And you decide I reject the null, you can make a type 1 error, cannot make a type 2 error, right? Because the type 2 error is failing to reject the null, but the null was actually false, should have been rejected. That was the wrong decision, right? So make sure we understand that before we start the problem, there's 4 ways it can go. You can reject and that was correct, reject and that was wrong, fail to reject and that was correct, fail to reject and that was wrong. Once you've made a decision, you can only make one type of error. So always be thinking about that. If you decide to reject the null, you can make a type 1 error, you cannot make a type 2 error. And so then if I were to follow up and say, what type of error could you make? If you've rejected the null, you'd say, I could make a type 1 error. Then you could write out that type 1 error like we did in the examples previously. I could say, what's the probability you make that type 1 error? And you say, it's equal to whatever the significance level in the problem is. Right, so we default to 0.05 if we aren't given one, or you'd use whatever was given to you in the problem. It said alpha equals 0.01. You'd say there's a 1% chance of making this type 1 error. And then conversely, if you fail to reject, right, if you fail to reject because your test statistic did not fall in the rejection region, you had a large p-value, you could not make a type 1 error. That's not possible. You could only make a type 2 error, right? Because you've decided to fail to reject. So the only error you can make is the one in which you failed to reject. And then you could be right or wrong, right? You're 50-50, right? Off the top of your head, you're thinking, yeah, I'm 50-50, right? I could be right, could be wrong. But then we say, what's the probability? You say, oh, actually, I'm not 50-50 on that, right? The probability of making that error is beta, whatever beta is, right? Now remember, just stop right at beta there. We're not going to calculate that in this course. So when we say what's the probability of you making a type 1 error, if that's the reality you're in, you can give me a number. It's whatever alpha is equal to. When we say what's the probability of making a type 2 error, it's beta, whatever that is. Again, hopefully it's not 50%, right? Hopefully it's less than that. And you won't have a number to give me, okay? And so just to kind of wrap that up, I want to make sure we understand alpha plus beta does not equal anything, right? There is no scenario where I can just do simple arithmetic and calculate what beta is from alpha. There is a way to find it, but it's a little bit more complicated. So if I have a significance level of 10%, that is the probability that I make a type 1 error if I'm in that world, but it does not directly and easily tell me what my power is. It does not tell me the probability of a type 2 error, right? We would have to be either, for this course, we'd have to be given that, as a follow-up. In this case, we did some research and we found that beta is 5%. If beta is 5%, what's your power? I know power is 1 minus beta, that's 95%. Okay, so there's a lot happening there. Really dense materials, so maybe go back and rewatch some of these things. A lot of these are very confusing concepts. Just want to, again, make sure we understand we can't just easily get alpha and beta from each other. They do affect each other, as we talked about. As one goes up, the other goes down, but it's in more of a complicated mathematical way than just, oh, I know alpha is 5%, so that means that beta is 5% too, or that beta is 95%, right? That would not be the case. Okay, we can't just easily do that. So again, make sure we can identify those type 1 and type 2 errors, as we did in the previous examples. And then once we get to the end of the problem here and you say, I've rejected the null or I failed to reject the null, no, there's only one type of error you can make because the other type isn't possible based off how we define those errors.